How can I start it? Because the other way. Okay. So, first of all, I would like to thank the organizers of this project on fractional differential equation, and of course also to thank for this fellowship that gives me also the opportunity to give this second or third talk here. And I apologize for those of you who has already heard some part of this talk, because I was told to be as much as general and possible. So I would like only to give some examples and some insights in the link between non-local differential operators and the theory of stochastic processes. So I will start with some background, some definitions, in particular on some stochastic processes, and of the differential equations that are linked to these stochastic processes. And I will start with non-stochastic differential equation, but ordinary differential equations. And then I will introduce, of course, some non-local differential operators, in particular some fractional operators that probably most of you already know very well. And then I will show the relationship with the Lévy processes, and in particular with a subclass of Lévy processes, which is called the class of subordinators. And then I will show some, as I said, some examples. So it's not an exhaustive review of this subject, but only some examples of the use of non-local differential operators in the theory of stochastic processes. So I will concentrate only on two classes of stochastic processes. The first one is the class of renewal processes, and the second one is the diffusion and then the Brownian motion. And then we will see how using non-local differential operators we are led to anomalous diffusion models, both in time and in space, fractional both in time and space. And at the end, if I will have time, I will also show an alternative perspective. So when we use non-local operators, but inside the stochastic stochastic integral. So we start with a very, very basic model, which is the model that you know very well, which is the Brownian motion, probably the easiest, the most important process. In particular, I will restrict only on the one-dimensional case, so the very, very easiest case, and so we know that for a standard Brownian motion starting from 0, this is the transition function, and the most important thing for us now is that this function here is the solution, coincides with the solution to the so-called heat equation here, where we have the first order derivative with respect to time and the second order derivative with respect to space. Of course, if we would be in a higher dimension here, we would have the Laplacian operator. But as I said, I'm only in dimension 1. And here, of course, you have the conditions, both initial and boundary conditions. So some very well-known facts about Brownian motion. In particular, the Brownian motion, the increments of Brownian motion are independent when they are taken over non-overlapping intervals, so on disjoint intervals. And also the BDT, the Brownian motion, is said to be Markovian in this sense. So the knowledge of the past history of the process influences the probability of being at time t at a certain point or in a certain interval only through the last known position. So, for example, in S less than t, the time t. As you can see in the density of the process, the variance of the process at time t is equal to t, and this is the characteristic of standard diffusion. And here just some well-known behavior of the trajectories of the standard Brownian motion. And the other class of processes I will concern with is the class of renewal processes, which is a class of, again, of Markov processes, but now, first of all, the state space is non-continuous, and we start, in order to define this class of processes, we can start by considering some IID random variables, so independent and identically distributed random variables that I will denote by zeta j, and I will denote by tk the sum of these random variables up to k. So then we can define the process n of t, which in the standard case will be the well-known Poisson process by this definition. So n of t can be described as the counting process of the process that counts arrivals of successive events. And the zeta j are called the inter-arrival times. So the zeta j is the length of the interval between the arrival of the jth and the j plus 1 event. In the standard case, in the standard setting, it is well known that we assume that the inter-arrival times, so these intervals zeta j, are distributed as an exponential random variable with parameter, for example, lambda greater than 0. And in this case, we are in the standard setting of Poisson processes. And what is important for us in the following is that this tail distribution of the inter-arrival times under this assumption is the solution of the standard equation that, differential equation that I will call a relaxation equation under this condition. And again, the increments of the Poisson process are independent over non-overlapping intervals. The increments, yes, and the process is again Markovian. So basically, these properties and the lack of memory property is a consequence of using in the equation here the local operator equal to the first order derivative. This implies exponential inter-arrivals and then the lack of memory. As we have seen in the case of the heat equation, it was similar to what happened there for the Brownian motion. And in the heat, since in the heat equation we had again a first order derivative with respect to time. So we are interested now in understanding what happens if we replace the first order derivative both in the relaxation equation that I mentioned just in the previous slide with a non-local derivative, non-local operator, which I define in a minute in the next slide. what happens is that we move from the Poisson process setting to a more general renewal process. And in the case of the Brownian motion, we have a similar modification. If we substitute, if we replace the first order derivative here with respect to time with the same general fractional equation that I will define soon. Or another situation is when we replace instead of the first order derivative, the second order derivative with respect to space. Here the definition is different. The definition of the non-local operator that I will use will be different. So first of all, of course, we must see some definitions for these non-local operators. Okay, so the very most well-known operator, fractional derivative in particular, is the so-called Riemann-Liouville fractional derivative. In this case, I have chosen the particular case where the order of the derivative is in 0, 1. And the space and the definition of the fractional derivative is on the whole real axis R. Another very famous fractional derivative is the so-called Zerbashan-Caputo, or simply Caputo fractional derivative. In this case, we are only on the positive semi-axis, real semi-axis, and again, alpha is in 0, 1. So as you can see, both are convolution type operators. So they are no more local operators as the first order derivatives, but they are defined by means of integrals with a certain kernel. Of course, we should give some conditions on U, but I will not go into details too much. Another very famous fractional operator, which I will not speak about it, but I just recall for completeness, is the fractional Laplacian on Rn. There is a huge literature on this, but since we will be only in one dimension, I will not use this operator, even if I will consider a particular case in some sense of the fractional Laplacian, which is the so-called Ritz-Feller derivative. So when we will replace the second order derivative in the heat equation, we will use this operator here, so-called the Ritz-Feller derivative. In this case, it is on R. And in this case, the order alpha is in 0, 2. The definition of the Ritz-Feller derivative is given in a different way with respect to the previous one, because it is given by means of its Fourier transform, Fourier representation. So pseudo-differential operator A can be defined by means of its Fourier representation in this way. And in this case, the A hat, which is called the symbol of this differential operator. And I will denote by hat the Fourier transform of a function or of an operator. So the I forgot to tell you before that, so I go back to the previous slide, that in this case, in the case of Riemann-Liouville fractional derivative, and also in the case of Caputo fractional derivative, the limiting case alpha equal to 1 reduces to the, in the limiting case, these two fractional derivatives reduce to the first order derivative. While in the case of the Ritz-Feller derivative, we obtain the second order derivative when alpha is equal to 2. So in this case, here you see, in fact, the Lévy exponent of the second order derivative. And so, okay, but we will use it later. Here you have some very well-known, some of the books where you can find a lot of properties and a lot of material on all these definitions. As I mentioned before, I want to use a more general definition of fractional derivative, which was introduced in well, more or less 10 years ago. Which generalizes, in particular, the definition that I've chosen here generalizes the Caputo fractional derivative of order alpha. If you remember, in the Caputo fractional derivative, we had here t minus s to the power minus alpha divided by gamma 1 minus alpha. Oh, yes, it's written here. So this, of course, is a generalization of this fractional Caputo derivative of order alpha for a more general kernel here. Of course, we must add some conditions on this kernel. It must be non-negative and locally integrable function on R+, and then we will see other assumptions that must be satisfied in order to have also a right inverse of this operator, of this, in some sense, derivative. So here in the symbol of this operator, I put this phi, which is not an order of difference of derivative, as in the Caputo classical case, but it refers to the kernel that I choose for this operator. So, as I said, we must have more assumptions on the kernel phi, and on its, in particular, on its Laplace transform. So I will denote by tilde the Laplace transform, in this case, of the kernel phi. And but they are quite technical, so I will not go into details. But under these conditions, this derivative here possesses a right inverse, a well-defined right inverse, which is defined in this way. And then also the theorem of fundamental theorem of fractional of calculus holds true. And then we can use this operator here. Also, the Laplace transform of this operator is well known and is written here. And it is an important tool for us in order to use this operator in the inside these differential equations. So just very, very shortly, because I see that all of you are expert in Levy processes. So just to introduce the notation, this is the symbol of a Levy process. This is the well-known Levy-Khinchin expansion of its characteristic function. This is the Levy measure, mean. But in particular, as I said, we will concentrate on a particular class of Levy processes, which is the class of subordinators. So subordinators are non-decreasing Levy processes, which with this Levy symbol here, and in particular, B must be greater or equal to 1, and the Levy measure must be concentrated on the positive semi-axis. Examples of subordinators are the Poisson process itself and the gamma process, and what we will use later, the alpha stable subordinator. I skip this slide, and then we have the first link between the theory of stochastic processes and the general fractional calculus theory. This is given by the kernel of this of the derivative. If you remember, phi is the kernel of the general fractional derivative, d phi of t, for example. So if we choose this kernel equal to the Taylor-Levy measure of a subordinator, then the Laplace exponent of the corresponding subordinator will be this quantity here, the Laplace transform of phi multiplied by theta. And this is crucial for us because I will show you in a minute. But before I must define the inverse of this subordinator. So h phi is our subordinator, so our non-decreasing Levy process. And we can define the heating time process. So it's the process that represent the first time where the subordinator hits a particular level. I will show you later some plots, some figures to understand better this relationship. But by now I tell you that I will denote by L phi the inverse subordinator, and by L phi xt its density. And this is the main fact, the most important fact is that it is well known that the density of the inverse subordinator satisfies this equation here, where we have here the general fractional derivative with kernel phi, and here the first order derivative with respect to the space argument, of course, under some initial conditions. In the special case where phi is again this power of t, power minus alpha, then, as I said before, the general fractional derivative coincides with the fractional derivative, Caputo fractional derivative of order alpha, and the Laplace Laplace transform of phi multiplied by theta coincides with the Laplace exponent of an alpha stable subordinator. Going back to the class of renewal processes, as I said before, we want to see what happens when we replace in the relaxation equation, very simple equation here, this time first order derivative, the first order derivative with respect to time by means of this general fractional derivative. And what happens is that we go from the standard setting of the Poisson process to a generalized renewal process. This is just the same slide that I shown before. So, of course, under the assumptions that I mentioned before, it is proved that this general relaxation equation under this initial condition has a unique solution, which is in particular completely monotone. And completely monotone function is a function that I forgot to put in the slide. A function f is completely monotone if it is for any x it is positive, and if it is of course infinitely differentiable, and the nth derivative of the function is greater or equal to 1 when it is multiplied by -1 to the power n. So given this characteristic of the solution to be completely monotone, it is possible to write the solution itself in this way, as the Laplace transform of the density of the inverse subordinator. And then, as a consequence, if we define a renewal process now we assume that the interarrival times are no longer exponentially distributed, but they have as a tail distribution exactly the solution to the previous relaxation equation. Then, since, as I said before, the solution to this equation is completely monotone, and then this, for it, this representation holds, then the following probabilistic representation of the renewal process n phi holds. So n phi of t is equal in distribution to standard Poisson process time changed by means of this inverse subordinator here, which of course depends on phi, on the choice of the function phi. As a consequence, n phi, the new process, the new renewal process, it's still a renewal process, as I will show you later, but it is no longer a Lévy process, and it is no longer Markovian. Of course, in some special case, for some particular choices of the kernel, we can give also some explicit expression, for example, for the probability mass function of the process, the probability of having k events at time up to time t. For example, in terms of this function, which is called a Prabhakar function, but there are many other results which are in this case more explicit. In particular, I can describe these results by means of this plot, since here we have an example of a trajectory of the standard Poisson process, and here on the right we have the instead fractional renewal process or fractional Poisson process when the derivative is taken equal to the Caputo fractional derivative of order, for example, 0.4. I've chosen this particular value because it's quite far from the standard case, which is given for alpha equal to 1. And then it is quite easy to see that the behavior of the trajectory is very, very different because, as I said before, the process is in this case equal in distribution to a standard Poisson process, but with a different time argument, a random time argument. Of course, this time argument is the inverse alpha stable subordinator, which is assumed independent of n. But this has the consequence that we have much longer interarrival times, since the distribution of the interarrival times now has infinite moments. And then the expectation of the interarrival time is the expected value of the interarrival time is infinite, and then we wait for longer time between one event and the successive event arrival. Then I summed up here what I've said so far, moving from this standard setting to the non-local relaxation equation, so with non-local derivative here. We have that the interarrival times are no longer exponential, but can be described by Mittag-Leffler distribution, and this introduces a memory effect in the process. So it is still our process now. It is still renewal process. So at time t1, t2, t3, when a new event arrives, then the process starts anew again. But for any other time, for example, at this time here, the process is no longer Markovian, so it doesn't lose memory, and only, but it is called semi-Markov process, since only the couple here, n alpha t and key t, which is this random variable here, so the length of this interval since the last event up to this time here, only this is jointly Markovian. Okay. So, of course, there are many other extensions of these processes, but of these results, but I will not go into details now. Since I want to move to the other model, which I introduced at the beginning, which is the Markov, the Brownian motion, and so I go back to the heat equation now. As I've shown before, I recall that the solution to the heat equation is given by the density, the transition density of a standard Brownian motion here. I recall that we are in one dimension, and again, the Brownian motion, it is well known that it is Markovian, as I said before. What happens if we introduce if we replace the first order derivative with respect to time? Oh, there is a mistake here. It is t, not x, of course. Sorry for that. For this, we replace the first order derivative here with respect to time with the Caputo fractional derivative, again with respect to time, of order alpha. Alpha is in 0, 1. Then, of course, we have not a standard diffusion in this case. In this case, we can still write the solution, the density of the process, for example, in terms of this right function or the Mainardi function, or another way. And we have still a probabilistic interpretation, a probabilistic representation of the process as standard Brownian motion time changed by this inverse alpha stable subordinator. So it's very similar to the case of the Poisson process. But in this case, we have, for alpha in 0, 1, we have a subdiffusion, since the variance or mean square displacement of the process is no longer t, but is t to the power alpha. And then alpha, recall, is in 0, 1 now. Okay, we have some particular cases, but I will directly go to this plot here, since here I would like to explain how the time change produces the effect of moving from a standard diffusion to an anomalous diffusion here. Subdiffusion in particular. Here I just draw an example of a normal trajectory of the Brownian motion, starting from 0. So BT is the standard Brownian motion. Here on the right, you have the plot of an example of trajectory for the subordinator, the alpha stable subordinator for alpha in 0, 1. So as you see, as I said at the beginning, the alpha stable subordinator is a non-decreasing Levy process, and since it is a stable, as a stable law, it has positive jumps at some random instant here. Here I plotted the corresponding trajectory of its inverse process. So I recall that L alpha is the inverse or heating time process the inverse of H alpha of T. So it coincides with the time of the first time where the subordinator hit a particular level. And then, since here we have some jumps, here we have plateaus in the trajectories of the inverse subordinator. And then, since, as I said before, the anomalous diffusion model, the B alpha, is equal in distribution to a standard Brownian motion time changed by an inverse subordinator. What is happening here is that we are considering this BT, but instead of considering the deterministic time T, as usual, we are considering as a time argument of B this inverse subordinator. So with this, constant piecewise constant trajectories here, and then what happens is that in some sense the clock, the time is stopping for some periods, and then this stops also the trajectory of the Brownian motion. Okay, this is simplified a little bit, but just to explain what is the effect of using non-local operator, and then from the stochastic process point of view, this entails that the time is no longer T, but it is given by this inverse subordinator here. Another way of introducing non-local operators in the heat equation is, as I said at the beginning, by replacing the second order derivative here by means of this Ritz-Feller derivative. As I said, this is the definition of the Ritz-Feller derivative here. For alpha equal to 2, this derivative coincides with the second order derivative, and then we are back to the standard setting. So while the solution of this equation is the density of the Brownian motion, we are interested in the solution of this equation, which in some sense is a model, an anomalous diffusion, a model of diffusion, but fractional with respect to space. But in this case, the things are quite easier, since the symbol of the differential operator that we are using here, the Ritz-Feller derivative, which I repeated here, coincides with the Lévy exponent of an alpha stable random variable. In this case, we are not speaking about, we are not considering a subordinator. So this is an alpha stable random variable with a symmetry parameter theta not equal to 1, as in the case of subordinators. So can be also symmetric. For example, we are back to the Gaussian case when alpha is equal to 2, and the case of a Brownian motion, and theta is equal to 0. Okay, but never mind. I can go directly here, and then in case I can come back. The space fractional diffusion is, in this case, we have still a Markovian process. Since it is the solution is a Lévy process, is the density of a Lévy process, and for alpha less than 2, so in the non-Gaussian case, the density of this process has fat tails, so it means that its tails, the decreasing of its tails for x going to plus or minus infinity is a power, has a power law behavior. And so the absolute moment of any order less than alpha is, it is very well known that for the alpha stable case is infinite. And thus the variance, the mean square displacement of the motion is always infinite unless alpha is equal to 2. So unless we are in the Brownian case. Here I go back to this slide here. Since here we have some trajectories, some sample paths of the space fractional diffusions for values of alpha greater than 1, in particular for alpha equal to 1.8, which is the no, this is the case which is closer to the Brownian case, while for alpha equal to 1.3 in red, we have the case which is more far than from the Gaussian case. And then here you see that we have some very high jumps, and so we are far from the Brownian setting in this case. So in the last minutes, I would just want to introduce an alternative perspective, an alternative way of using fractional or non-local differential operators in the theory of stochastic processes. As I said before, I have shown so far some cases of partial differential equation or differential equation, but deterministic differential equation, while here I'm considering integration or with respect to, in particular here, with respect to white noise. I start by considering the most well-known process in this setting, which is the fractional Brownian motion. The fractional Brownian motion with has parameter h in 0, 1 was originally defined by Levy in this way as an integral with respect to the white noise. For h equal to 1/2, we are back to the Brownian case, and probably all of you know that the fractional Brownian motion is a centered Gaussian process with stationary, self-similar but non-independent increments, unless h is equal to 1/2. And for h greater than 1/2, it displays, it possesses long memory, which means that the autocovariance decay for large time distances is power-like, so then slower than exponential. It's decreasing slower than exponential. But we will refer to a more general and bit more complicated representation of the fractional Brownian motion, which is due to Mandelbrot-Van Ness. So here, instead of the simple the Brownian motion that I have used so far, I consider a two-sided Wiener process. So for t in R. And then if we consider this integral with this kernel here, this integral with respect to w, then we have this representation of the fractional Brownian motion. This is a constant that we can now ignore it. What I want to show you is that this very well-known representation of the fractional Brownian motion can be written as in the last formula here, can be written as an integral with respect to W to the Wiener process W, but of this kernel. And in this kernel, we have this operator MH, which now I'm using a quite different notation, but this operator here for H less than 1/2 is exactly the Riemann-Liouville fractional derivative that I mentioned at the beginning. For H greater than 1/2, it is instead the Riemann-Liouville integral. So what we have here is still a non-local operator, but now we are using it in a completely different way, not in the equation governing the process, but in the definition of the process itself. So what can we do with this? We can go from the white noise setting to a more general noises. Of course, I should introduce some other notation, but probably I don't have enough time. I just, in this case, we can consider the space of the Schwarz test functions and its dual S prime. And then we can give a more general definition of the Brownian motion and, for example, of the fractional Brownian motion by means of this characteristic functional here. And again, it is crucial in this definition, the property of f being a completely monotone function. So recall the definition here. So if I consider f a completely monotone function on the Schwarz space on R, then we can define this characteristic function, and by means of the Bochner-Millos theorem, we can find basically an inverse of this functional here in the space SR in terms of this unique probability measure mu. So to give a simple case for when we choose phi equal to this functional here, then here you can recognize the characteristic function of Gaussian measure again. So the measure mu here coincides with the white noise measure, and so the space is the white noise space. Then we can go to other choices for this f. For example, we can choose the Mittag-Leffler function, and then the corresponding measure is the so-called gray noise measure. This is the general reference for this gray noise measure. And then also we proposed a different completely monotone function, which is the incomplete gamma function. So the upper incomplete gamma function can be defined in this way. It's very well known that it is this given by this alpha minus 1 e to the power. So this is the upper incomplete gamma function, and in this case, if we use this function here, then we can define of course under some other conditions, we can define another, in some sense, gray noise, and so on, so on. Of course, we can find other completely monotone function that can be used here. And this is the very last, I think, the very last slide, or more or less. We can, by means of what I said before, if we can define generalized process on the dual of this space by considering the dual pairing, we apply it to the indicator function here. So in the case of the white noise space, if we apply this dual pairing to the indicator function of the interval 0t, we are back to the standard Brownian motion. If instead we apply this dual pairing again in the white noise space to this functional here, where again here we have Riemann-Liouville fractional derivative or Riemann-Liouville integral, then we are back to the definition of the fractional Brownian motion that I have already shown. In the other cases, we have the so-called gray Brownian motion or gamma gray Brownian motion. Here some reference on all these processes here. So I think this is my last slide, and of course some references on some of the books and papers that I mentioned before. So thank you. So if there is any question, I don't know if someone is at home, I don't know.
I didn't give a comment. So it's just a question which somehow comes to my mind eventually, and then I forget about it. That, like to offer a question, possibly trivial, possibly not. When you're doing the subordination of this heating time of the subordinate, what you get, of course, is not Markovian process.
Yes.
Now, if you take heating time of the Brownian motion, then you do get Markovian process. So, what are the processes for which if you take heating time, then you will get Markov process?
I think it's only in the case of Brownian motion. Yeah. I think yes. Well, because in this case, as I said, you have again Brownian motion only in the case where alpha is equal to 1/2, because in this case you have Brownian motion and the time argument is reflecting Brownian motion again. Okay, now I understand your questions. Why it doesn't happen for other processes? Basically because the heating time of other processes are no longer, they are no longer Markov and no longer.
Well, anyway, that was.
Yeah. You're right. So yeah. Of course.
Other questions, comments? Yes, related to that. Renat theorem said that you relate multiple local times with the Gaussian process. And I think in the case of I think the characterization theorem says that in some cases the related process is Markovian, so that you can go back and say something about because the inverse polymer is just forgot. Yeah, there's a general theory
Yes, you're right. Yeah. Okay. Yeah.
Easy, well, to simulate the quantum.
I think yes, but I'm not a specialist on this, but I have seen a lot of, you mean not in the stable case, probably, in general cases. In some other general cases, yes, for example, the inverse of the gamma subordinator, I think I've seen simulations, not, of course, you must choose some some kernel file, some phi, yes. But I think it's not only in the stable case that it is possible to simulate, yes. In some cases it's easier, and probably in some cases it's not possible or it's not known, but the subordinate, you mean the subordinator with the subordinator itself, not with the inverse subordinator. In the case of the inverse, it is possible to simulate the inverse subordinator, yes. Not only in the stable case.
I sometimes worry about having both time and space fractional for some complicated physical phenomena. Has there been any work done on it? What kind of stochastic processes would that give rise to?
You mean when you jointly use the time and space fraction? Yes, yes. I didn't describe it here, but it is in the, for example, in the paper by Mainardi, and I don't remember exactly, but Mainardi Pagnini something. Yes, it is well known. Yes. In the stable case, but also in general, it is, yes, it is. Yes, yeah. No, because I was thinking that it was referring to the alpha stable case, but of course also in general, yes. I just concentrated on simplest case. Yes.
Okay, so fraction run motion, for instance, you can find a lot of approximation limit errors. There's run model and Berg model kind of thing you converge to fraction run motion. And I'm wondering if the fraction problem process is kind of a new object. Reference on some sort of natural district model converting to the fraction problem process.
Well, it is not very new, So there are a lot of results on it. Also on the, for example, continuous time random walk, when the counting process is fractional Poisson process, then you have a lot of limit results on it. So of course you can refer to also to the book by Merschaert and Sikorsky in this case.
But outside of that, is there other models also?
You mean models converging to the fractional Poisson? Sorry, I didn't understand you. Models converging to the fractional Poisson. I don't know. I mean. Okay, thank you.